Okay, this is the average value of function. It's still the chapter 6. Okay, so this is chapter 6, still chapter 6. It's the end of chapter 6. Okay. So if you're looking at the database, like for example in Excel, in Microsoft Excel, you know that if you have 10 students, in maybe the average score is 50, then the 50 is from the first students plus the second students until the 10th students and divide by 10, and you'll get the result is 50. So if we are dealing with the functions and we want to measure the average value, we get the average value if we are let the y is equal f of x, then the average value becomes the f of x sample points until the xn, okay, and divide by the numbers. And if we are dealing with the delta x, we can solve the delta x by divide b minus a over n, as we approach in our previous Riemann sum, okay. And we can substitute the whole n equal b minus a over delta x into our average value, and we can solve it, and it turns out we get the sum results multiplied by 1 over b minus a, and as the n approaching infinity, we get 1 over b minus a, and then the whole thing here, the sigma, is our integrations definitions, and this is average value of functions. Okay, and based on the average value, we also have mean value theorem. Okay, it's basically saying that if f is continuous on the interval, and then there will be c number in those intervals, such that the number of c is in between. Okay, is in between the a and b, and that c is equal to the average, in which we already defined before this expressions, and we can rewrite the integrations from a to b fx dx equal f of c multiplied by b minus a, and that's the mean value theorem. Okay, the next part is we will continue to, this is chapter 7, techniques of integration. The first integration techniques that I want to show you in this chapter is integration by parts. Let's consider the product rule. Okay, so if you have the f equal the big F equal to small f and g, and all the function is continuous and differentiable, then our product rule is f prime g plus g prime f. And let's write in terms of d dx and then integrate all. Okay, if we integrate, the left part is coming back to the original equation fg, and the other is becoming g df and then f dg, and we can write this in terms of f dg or g df if you want. That's the same thing actually, because fg is it's the same continuous functions, or similar, not exactly the same. And we can write this, and we can rewrite the whole complete functions. Fx g prime x, this is f, this is dg, okay, and this is fg, right, and this is gdf. Okay, and we can substitute u as f of x and v as gx, and we can rewrite them in u dv, integral u dv equal uv minus integral of v du. It's I think the most familiar one for you who have learned the integration by parts before. And for example, if you have integration of ln x dx, we can separate ln x dx become ln x and dx. So ln x becomes our u, we can find du, and dx become our dv, and we need to find dv. And based on these expressions, we can set some arrangement and becoming this is uv and this is v du. Okay, and we can solve that and come in this expressions. Okay, I think this is one of easy example. And the other part, if you have the ex sin x, it's actually ex is if we derive or integrate, ex will going in cycles or repetitions, right? So the first thing to note is you need to write the whole equations. For example, if you already define u is ex and dv is sin x dx, okay? And then this is the du, and then this is v. You can do both. You can use u as sin x or dv as ex dx. That would be the same result, I think. And write in the whole terms, okay? So this is the u dv, this is uv, this is v du, and we get ex cos x, and do the same thing, the integration by parts for this part, and we get this whole thing, okay? And notice that our original functions is ex sin x, and we also have at the right equation is ex sin x, okay? Now what we need to do is we move the ex sin x to the left side and become 2 ex sin x dx, and then we solve them by dividing by 2 and plus c at the end, and this is the answers, okay? Now let's look the x sin x dx, okay? My idea is to get the x is u and sin x dv, because x, if you derive, it should become 1, and if you derive once more, it becomes 0. So I believe that will be our initial choosing which one is u and dv. So you need to choose which one is, it can be easily derived, and if you can derive until 0, that should be really good results, okay? You will get a good result if you put x in u. So u equal x, and then du dx, and then dv is sin x dx, and then v is minus cos x. And we set up our arrangement. So this is u dv, and this is u, this is v, and this is v du, okay? And we can solve minus cos x, become minus sin x, and multiply by negative, it's become plus sin x here. And of course, in integration, if you want to check your result, you can check by deriving the first derivative of this expression, okay? I can solve it, and actually we are going back to our original equation, so this is correct, okay? Now the other one, notice that we have x with 4 and then ln x. The ln x, it's easy for ln x to be derived, right? So the idea for ln x to be derived is becoming 1 over x, right? And dv, I can integrate this and become 1 over 5 x5. And I can set up the integrations. This is u dv, this is u v, and this is v du. And set up the integration, and I believe it's not that difficult to integrate. And this becomes the polynomial, it's x4, and we get 5 integrations, and x to the 5, 1 over 2 5, and we get this as our results, okay? So notice that if you have ln, it's better for ln. So ln is better to be derived, okay? So this become 1 over x. And if you have sin x or cos x, this both can be u or can be dv, because it's easily to be derived and easy to be integrated, okay? But now in these expressions you have x to the 4, right? I said before, x to the 4 it will be really good if you can derive it. Like for example, you can derive until it becoming 0, but it takes a long process, and you see it has ln x. So that's why I'm choosing ln x as u, okay, because it's more easier for ln x to be derived than the x to the 4. Okay, that's a thing. Another necessary main idea of integration by parts. For example, if we have x squared sine 3x dx. Okay. So let's see here. Okay, I have u is x squared and dv sine 3x. Okay, and it's becoming 2x, and it's becoming negative cos 3x over 3. We set up the integrations. This is uv, this is v du. And again, now we are getting this expression in which we need to integration by parts one more. Okay. Okay, by doing so, we then get these whole expressions, and we still have sine 3x 2 over 3 integrations. And we need to solve this and becoming this cos 3x at the very end. Okay, so at least we have integration by parts 1 and 2. Okay, the whole thing here. Now the results, we can set up all the terms, the second terms and then the third terms, and plus c. And then I'm asking at the very end here, can we simplify the method? Okay, notice that the uv and v du is actually our just arrangement. Okay, arrangement from our product rule and integrated product rule, right? So let's see here what I mean by the arrangement. So we set up, we call the left part is d and the right part is I. D is from differentiations and I from integrations. So di, or we call this is di method, is some set of arrangement of a part of the integration that we can derive, and apart from that functions can be integrated, which means it's actually our arrangement of uv and v du. Okay, and if we are setting this d as our x squared, so it's become 2x, become 2, become 0, and this positive, negative, positive, negative is from these expressions. It's having positive and negative, right? So positive, negative, positive, negative. So if you still have integration by parts here, it will have another positive, negative, and positive, negative if you still have one, more and more and more by parts, right? So that's why what I'm doing here, I'm giving positive, negative, positive, negative, and then what we are going to do is we are multiply this with this and multiply this x squared with negative cos x. Okay, multiply negative with this and multiply with here, and we are setting up all the x squared and minus cos x become these first terms, and 2x and sine x negative, and negative is become positive, it's 2x sine x, and 2 cos x is become positive, and that is our answer. And you can check if you derive this and it will return to our original equations. Okay, here if you want to break down by the integration by parts traditionally, so this is u, this is dv. Notice that this u and v and du are a setup of arrangement of what we did before, the di method. Okay, so this x squared cos x, and this become the integrations of the 2x minus cos x, and this is again integration by parts one more, and it become 2x 2, and then dv is minus cos x, and v become minus sine x, and we can set up its arrangement is 2x sine x and 2 minus sine x, right? And of course the last part is just 2 minus sine x become 2 cos x, right? And what we did is because it's having 0, that means the last part here is 0, so there's no other parts after t to a cos x, okay? And that's why by this traditional method we can confirm that actually what di means is we are just setting up all the udv that possible. So if you have udv inside udv inside udv, you get like plus minus plus minus plus minus and more terms, and the integration become a long integrations results, okay? So that's the di method. And the other necessary thing that I want to show you is if you have the integration secant squared, you can easily get tangent, right? But if you get the secant x, the idea for secant x is from, if you derive the secant x, and it will be secant x tangent x, right? And if you derive the tangent or the tangent x, okay, it's become the secant squared. Now you see this having secant x is having secant squared x. If I'm going to secant, and then this becomes secant x plus tangent x, if I'm multiplying both of this, this become this, right? Secant squared secant x tangent x. Now I have this secant x and I want to make this second part here, in which if I'm going to integrate, I can integrate easily and becoming either secant x and tangent x, right? That's why the first thing that I need to do to solve this secant x is multiply with the secant x plus tangent x over secant x plus tangent x. And I get the secant squared plus secant and secant tangent, okay? And secant squared secant x tangent x is actually, if we are deriving the secant x plus tangent x, is actually secant x tangent x plus secant squared x, in which we are getting this result, right? So actually what we did is, if we derive the whole thing at the bottom functions, the first derivative becomes the top one, right? This secant x becomes secant x tangent x becomes secant squared x. So I can substitute and the whole thing become 1 over u du, and we can solve 1 over u, it become ln, and substitute back the secant x plus tangent x, and we get the results, okay? Now the secant cube, based on our results before and integration by parts, I can solve these two and separate, become secant x and secant squared x. And using the integration by parts, I can get this arrangement, okay? And then I can make a substitute the tangent squared and make it all secant. It's becoming secant cube minus, it's minus or positive, and then secant x tangent x plus, okay? And then the second x we already solved secant x, it's secant x plus tangent x, and this secant cube here is the same as our secant cube in the question, so I can move that to the left hand and becomes 2. So the whole equation become half secant x tangent x plus ln absolute value secant x plus tangent x, and a plus c at the very end. Okay. Now the next section will be called the trigonometric integrals. This is actually the second, and then the other section will be trigonometric substitutions. Okay. So the first case is if you have sine with the power of m and cos with the power of n x dx. Okay. I will give you the example first. So sine 5x cos squared x. So the idea is, let me write sine squared n squared is become actually sine 4, and the other sine is writing here. Okay. And I can rewrite the sine squared become 1 minus cos squared and sine. And because cos and sine is interchangeable if you derive, and you can substitute with u, and then the whole thing become the x become minus sine minus 1 over sine x du. And substitute du, it become 1 minus u squared, and then squared u squared du. And this is the expansion, and you can integrate and you will get the results.